So do you see my screen?
I do. I can see that. And I have started the recording.
Yes, we can see.
Okay, perfect. So I would like to give this introduction into RGB technology, explaining the way it is designed, explaining all the terminology layers behind RGB, how it is built out of those layers, and how it can be used by wallet developers, by those who would like to integrate RGB into the exchanges or payment system, or just to play with this new thing. And unfortunately, I wasn't able to fit it into a single 1-hour presentation, so it will be 2-part at least. The next week will be the second part. And today I have something about 70 slides, which I hope to finish throughout 1 hour. So what is RGB? You all know this. I will just really briefly cover that for anybody else outside of RGB community who will be watching this presentation later. RGB is basically, well, we name it a system for digital assets or for tokens, but I would like to, I prefer to name it more broadly. It is a smart contract system that is able to manage rich state, and assets is just as one example of that rich state. There are other examples like identity, and maybe a few more will appear once the technology will be launched. The most interesting thing about RGB is that it uses client-side validation paradigm proposed by Peter Todd quite a few years ago. And the data, they are held by a state owner. Like if you own assets, you have your own data that are proving and defining your ownership structure. And they are not kept in some public consensus like blockchain. So it's a non-blockchain technology. It is using Bitcoin blockchain, but more importantly, it's not using just a blockchain. It uses Bitcoin transaction graph. It is built on top of Bitcoin transaction graph, the graph of the transactions. And it allows it to work both inside Bitcoin blockchain, on-chain part, or with a Lightning channel, because Lightning channel have also transaction graph. So RGB is abstracted from the blockchain. It operates on the transaction graph level, and it just trusts either Bitcoin core or Lightning node that it does provide a correct information about the real Bitcoin transactions. So RGB doesn't have anything to do with the blockchain itself, but it uses Bitcoin and Lightning Network security model to do the actual commitment and creating a verifiable and provable history of state ownership, asset ownership. And we hope that quite soon Blockstream will launch the Simplicity scripting language, a formally verified language, which is very good and advanced. And we are ready for using Simplicity script as a part of RGB system as well. The main properties of RGB are confidentiality, safety, scalability, low Bitcoin blockchain congestion, and it is future ready and will be able to work hopefully many, many years without hard forks happening. I will quickly cover these properties. Well, it is confidential at multiple levels. Data is known only to owners of asset, owners of state, and not the entire world. If the owner would like to share the information with some other parties, they will also know that, but not before that. You don't have some on-chain analysis tool or online explorers that will show all transactions for all assets. There is no such place in RGB to look into. Amounts are also confidential. We use person commitments and bulletproofs, a combination of the best parts of Liquid and Green, because Liquid uses Pedersen commitments with an older version of French proofs, Bormian signatures, which are quite large, and Green uses bulletproofs. So we have been combining these two strains, getting this hybrid, quite advanced confidentiality. We also merklize a lot of data structures. So future owners of some state, they will see the history and they will be able to verify it. But because of partial reveals, they will see only a tiny part of the history that is really required for the verification. The rest of history will be hidden from them. And that's why we have these quite complex concepts of partial revealed and disclosure and not fully revealed information, which one of the reasons why we have quite a complex protocol. But we really believe that confidentiality is a very, very important part of the system. And no RGB specific data can be extracted from either Bitcoin blockchain or Lightning channel transactions. So if you look into blocks or into Lightning channel, even if there is a lot of asset moving happening, you will not know about that at all until you have the historical data from asset owners. So it's quite advanced confidential model, as you see. Also, it is quite safe because, first of all, the most part is relying on blockchain underlying Bitcoin and Lightning safety assumptions. The second is that we isolate state between different smart contracts. So if you have two different assets issued by different issuers, they don't interact directly. They never mix their data, and the code never works on two of the contracts, and they never cross-validate. There is a way to exchange assets, for instance, with the things like Spectrum protocol, but it's done as a layer on top of Lightning Network, and it is not related to RGB itself. So basically, it uses Lightning Network cooperation between different transaction graphs. Like if you do a multi-hop payment with a Lightning Network, one transaction graph of one state channel is not directly affected by the data from the transaction graph of the other channel. They are all communicating through the messaging P2P protocol, OMNI, onion routing protocol. And the same way it works for RGB with the Spectrum. And it is also quite strong in terms that RGB constructed in a way that you can prove formal statements against the smart contracts and their history, both with the simplicity language and with the overall design of the structure of RGB data. It is scalable because of different things. First of all, it is not limited by blockchain. It can operate on top of Lightning channel or any other payment or state channel. I hope in future we will have more complex Lightning channels like multi-party channels. And it can work on that. Anything that supports a transaction graph is suitable. Hello? Somebody is trying to ask something? I have some strange echo. Okay, I will try to continue. Amount of data kept by clients for full validation are significantly lower than in case of blockchain-based smart contract systems, any of them, because they keep the history of all the smart contracts, even the one that they don't use, for all the time. Here you can prune the history, you keep the data related to the assets you own at this particular moment, so the size is much smaller. And we use something like smart contract level sharding. The sharding is a wrong term, and I don't like it, but people understand it. It's basically that all smart contracts, they have absolutely individual and independent history, and they not cross-sect anyhow. So this helps in scalability. There is no congestion of inside Bitcoin transactional graph. First of all, because of that, you are not able to extract any information about RGB from Bitcoin or Lightning channel. But from the other point, you don't add any data, like any size of data. You add information, but unsized and hashed information, which basically says nothing about the source of this data. And it can be detected that this information is added before you obtain the proofs which are kept private by the state owners. And as I said, it is future ready. It will require no changes at all with the Taproot release, Schnorr release, L2, multi-party Lightning Network channels, discrete block contracts. It will work on top of them once the software will be out there. What is possible with RGB? You can issue fungible assets or securities, digital securities, even complex forms like options, futures, centrally or federated issued, anonymously or publicly, with possible secondary issuance, demurrage, inflation, and many, many other programmable and manageable properties. Different forms of bearer rights outside of assets and securities, like voting rights, non-fungible assets, tokenized art or game collectibles, decentralized digital identity and key management, and hopefully many, many more applications. I frequently get the question how RGB is different to existing other tokenization technologies, and here I summarize this information. Comparing to liquid confidential assets, RGB works with Lightning Network. It's the most important property of it. It replaces large Borromean signatures with a model bulletproofs. It does not consume any space in blockchain. Actually, even if federated blockchain, it has a space consumption problem. So RGB doesn't occupy any space in any chain. It has a universal smart contract language, again developed by Blockstream, and the most parts of RGB actually were originally created as a part of liquid technology or Blockstream technology, but it's all open source, so we tried to take the best from what it was existing. And it works on Bitcoin mainnet, doesn't require federation, which is another important property. Comparing to OMNI layer and others like counterparty colored coins on Bitcoin protocol, we don't use blockchain space at all. They do. We have much higher privacy and confidentiality level, and we work with Lightning Network without modification of the Lightning Network standard structure, and that's quite an important part of the story. Comparing to Ethereum, EOS, and others, Turing complete smart contract systems or corporate blockchains even, first of all, RGB is not a blockchain, and that's very important advantage. It works on and only with Bitcoin, the only censorship-resistant, unconfiscatable hard money. So I think that renders basically Ethereum and other system quite useless. Now coming back for the actual topic, the technology behind the RGB, I would like to start with architecture overview. In designing and doing RGB, we used a paradigm-based approach. It was basically this way of doing things was proposed and strictly proponed by Peter Todd, who was one of the people behind the initial RGB vision, the vision behind the client-side validation. The concept, it's quite different to many other systems being designed in the sphere today in a way that basically we try to isolate different parts of the system through the abstraction and integrate these parts through very strictly defined interfaces. Those who will be looking into the source code and documentation, you will find that RGB is a set of standards. And inside the source code, you will see we have a folder called paradigms, implementing a number of paradigms. And each part of RGB follows some specific paradigm and can interact with others only through the interface defined within the paradigm scope. And it really helps to audit the security model. And the idea of Peter Todd is that a properly designed API structure may help to prevent developers from doing mistakes with the technology, from doing some leakage of privacy data or some breaches to the security model. Of course, we still have that chances, but they can easily be audited, isolated, and prevented. So that's why we stick to this idea. And there is 4 main paradigms used by RGB, which are very important to understand. They are all independent from each other, completely independent, and they are assembled in some singular system at the level of RGB itself. These paradigms, they are not even Bitcoin specific. It's a kind of development, coding, architecture paradigms that can be applied to many systems outside of Bitcoin, even outside of Bitcoin itself. So these paradigms are, the first one is a strict encoding. The concept that we should use very formal, well-defined practices of the data serialization and deserialization, encoding and decoding, such that they will work the same way, deterministically, with the same way on any computer hardware, including present and future, over the network and so forth. With the client-side validation, it's really important to be sure that the data saved today will be read and verified by all parties for eternity in the future in the same way. And that's why strict serialization rules, strict encoding rules and practices are very important to make sure that this data are always interpreted in the same way by all parties. It is a consensus critical part of the system. The second one is single-use seals. Single-use seals is an idea. It's a development of cryptographic commitment protocols in a direction that you can actually commit to do a commitment. And single-use seals can be created on different forms of medium, even centralized medium. Peter Todd was saying that you can do single-use seals with the New York Times newspaper. I mean, printed newspaper. So it's another paradigm, quite unusual and non-trivial, which I will be explaining later, and I will be showing how actually RGB is applying single-use seals to Bitcoin transaction graph as a medium. Cryptographic commitments, well, it's quite known cryptographic concept. We a bit extended into creating some sort of new concept named embed commit verify scheme for cryptographic commitments. And with the cryptographic commitments, we are able to commit to some data, namely the state of RGB, the assets, the ownership structure, and many other things, and embed that commitments into a transactions. The commitment is actually a thing where you can, if you have some data named message, and you create commitment to this data, from the commitment itself, you are not able to get any knowledge about the original message. You can't guess anything about that message. With an embed commit scheme, you can't even know that there is a commitment inside a container. And however, if you have the original message, and in case of commit embed scheme, a proof, you can use them and deterministically make sure that there was a commitment, that the party who created commitment know that message at some time in the past. And basically, that's what cryptographic commitments is about. The last concept is a client-side verification, which, again, three of these concepts were created by Peter Todd with his significant help. It's a concept by Peter Todd, and I'm not able to explain it in a one sentence, so I will talk more about it when we get to the appropriate section of the presentation. The code covering these paradigms can be found in GitHub with this link. You can, it's quite extensively documented. You can read through it and get more detailed technical impression of how they work. RGB is basically these paradigms, which lies outside of the scope of Bitcoin, applied to Bitcoin transaction graph, not Bitcoin blockchain, but Bitcoin transaction graph, which may reside in both Bitcoin blockchain or Lightning Network channel. It uses specific RGB consensus encoding defined in this specification LNPBP 10 and in the code by this address within the Rust LNPBP library. It takes single-use seals and apply that to Bitcoin blockchain, creating transaction output-based seals, another standard, and code reference. It uses cryptographic commitments in two ways. First of all, to create deterministic Bitcoin commitments defined in the LNPBP 1, 2, and 3, and in Bitcoin BP DBC module of Rust Lightning library, and multi-contract commitments. The thing that is used for this so-named sharding and contract isolation is defined in LNPBP 4 standard and the module named LNPBP 4 after the standard. And client-side verification with the RGB schema and RGB contracts, which I will be covering later. And how these paradigms are interrelated between themselves and with these three layers. Basically, we have three verticals: paradigm vertical, Bitcoin transaction graph vertical, and RGB. And only the later one is RGB specific. The first two, they can be used, the paradigms, they can be used even outside of Bitcoin. And Bitcoin transaction graph defines systems that are general to Bitcoin and different future layer 2 and layer 3 applications. So with the strict encoding and cryptographic commitments, we use both of them to build a client-side validation. In the rest, these paradigms are very different and independent. With the cryptographic commitments, we create deterministic Bitcoin commitments. So it is the way how we commit and bet into Bitcoin transactions and parts of Bitcoin transactions. And using single-use seals applied to Bitcoin blockchain and deterministic commitments, we build transaction output-based seals. It takes off seals, a case of single-use seals built with the deterministic Bitcoin commitments. The next, we use strict encoding and cryptographic commitments to create parts of RGB named consensus encoding for RGB and consensus commitments for RGB. And next, we use, again, transaction output-based seals to build state transitions and different structures of RGB protocol. I will be covering them later in more details. What are these anchors, assignments, consignments, transaction, stashes, and the rest. And with the client-side validation, we built, again, the structures and the schema. I would like to point out that consensus encoding and consensus commitments, while they are used by transitions and RGB data, they are not used directly, but they are used through this paradigm integration at the level of paradigms calling each other. And all that together allows us to reconstruct RGB contracts and stash. Basically, the difference is that RGB contract is some contract defined. For instance, it can be a contract defining asset. And this contract is dealing with a single asset type it defined, and it has a history in the future. And there may be multiple contracts, and you may own multiple instances of some asset under the contract, one contract, and some other instances of some other asset under other contract. And there could be multiple contracts we are working together. And all these contracts, histories, and related data, they constitute what we call a stash. And a stash is actually all the data related to client validation of RGB data that's owned and held by a specific party, for instance, a wallet. What is RGB Schema? RGB Schema is a blueprint. It's a standards for constructing RGB contracts. You may think about them as an IRCs for RGB, like IRC20 defines a token standard that can be used by wallets and exchanges to integrate any Ethereum contract that issues some tokens. In the same way, we have we have a fungible asset schema that defines a standard for RGB contracts, and all wallets that are supporting RGB fungible asset schema will be able to work with any of those contracts issued by different issuers. The other example of schema is, for instance, collectibles, or there will be a schema for digital identity. Issuer defines issuance contract, but for being supported by wallets exchanges, it must stick to a particular schema that is used by these wallets and exchanges. And wallets, when they get information about some asset, one part of the validation process is basically that they validate the data they received and the contract against this specific schema and work with them, accept them only if it passes validation. The RGB as a technology is quite complex, and today I will mostly cover what we name a core library. It is a part of LNPBP library. It's a core RGB library, which is very low level. It gives you a very low level interface, which is mostly useless for wallet developers because it's very complex. They have to do quite advanced stuff. So to abstract that, we will be creating, and we are already creating, so-called schema-based libraries. It's so if wallets would like to use RGB assets, they don't need the whole nearly unlimited RGB functionality. They need just to work with the RGB contracts that are done according to fungible asset schema. And the library will provide them with an asset-specific function. So instead of working with RGB state, which can be quite generic and not even related to some assets, amounts, and so on, they will be working with assets, a particular form of RGB state defined by RGB schema. So that's the way we are planning to help wallet developers with integrating this quite complex client-validated thing. So for this reason, we are defining like 3 layers of abstractions for RGB. The most low level, it's on the top of the slide, is the LNPBP core library, which I just explained to you. It's very low level. It is very conservative. Namely, once the library will be released, it is the library we've been put most of our work into, and we hope that at the end of this week, next week, we will have a beta for audit. And once this library will be released, there wouldn't be no more a lot of new functionality coming to there. There will be some bug fixes and maybe some small improvements, but RGB at that level would never ever change, hopefully, once it is released. On top of that, all of the changes to RGB from that point will be coming through the schema, because schema and RGB contracts. Because simplicity language, which is Turing complete language, will be used in both schema and RGB contracts. We would be able to bring new type of data structure and new types of complex validation rules through the simplicity language and not core RGB library.
Well,
On top of our,
sorry, if I may interrupt, there was a question at the beginning about simplicity. Are you sure that simplicity is Turing complete? Because one person thought that they made a big deal out of it with no having loops.
Well, when I talk about Turing completeness, not in this scope, but to some academics and computer science expert, they always laugh with the way people use Turing completeness term, because basically there is no fully Turing complete languages per se. And there is a simple definition of Turing complete language, is basically that it is a language using which you are able to create an interpreter for the same language. Basically, I wouldn't guarantee that simplicity is formally strictly Turing complete, but I'm quite sure that the functionality of simplicity language is sufficiently extended is sufficient for creating very complex asset behavior rules, which are much more advanced than the ones that are created with Bitcoin scripts. Coming to the loops and this part, well, basically with the blockchain type systems, we already have seen that in all these Turing complete languages, you are not able to have unlimited loops as well. Well, technically you can write them, but they wouldn't simply work. So I think it's a common property of all languages that are related for consensus-based systems. Okay, I will continue. So on top of this RGB core, LNPBP core library, we are already building RGB standard contracts. It is a library implementing the particular schemas for fungible assets, for collectibles, and we will start with the fungible assets. And it's a mid-level where you can directly move assets and construct arbitrarily complex asset transfers as a wallet developer. So you have a very granular control, but for a single specific type of RGB contracts. It's a mid-level, it's still quite conservative. It will be provided with the WASM buildings and C buildings. So there will be, in the second column, you see the SDKs, and basically I'm basing on this library. We will do RGB SDK with the JavaScript, Swift, and Kotlin. So mobile, web, and server-side developers will be able to use the RGB, which is written in Rust, not through a low-level stuff, but through a more high-level native code. And there will be also this kaleidoscope and command line tools which help people to issue tokens, play with them, and do transfers. As I said, I hope that we will be releasing on the 1st of May the initial public version of Kaleidoscope to do that. And the third layer is RGB Wallet Library. It is a high-level library. The difference with the previous one is basically if you're a wallet developer and just would like to have a simple API where you say, let's transfer 1,000 of USD Tether to this guy, and you don't worry, and you don't want to worry about coin selection algorithm, how to store the data, how you just need to do that transaction, because the transaction can be done in a multiple different ways. With a library, previous library, you are able to control that granularity. With a high-level library, you will just say, and you propose with a single variant, which is very basic, but is sufficient to do simple and quick integration into a wallet. And there will be also a SDK for that. That additionally to the previous SDK will provide with the tools that will be automatically managing storage of client-validated data and network interfaces for you. So you don't need to worry about that part of the development. Oh, so now we're actually getting to the next section where we'll be covering more details about RGB itself. We have basically, as I said, we are working with Bitcoin transaction graph. Here on slide, you see that orange block, large orange block. It can be based both on Bitcoin blockchain and Lightning channel. So I would like to emphasize this one more. Everything that I'm talking here works both with a Bitcoin and Lightning node in exactly the same way. You just change a backend provider from Bitcoin core to Lightning node, and the library actually is completely abstracted from that stuff. And on Bitcoin blockchain, we build these two implementations of paradigms, single-use seals with transaction outputs and deterministic commitments. And on top of that, we're building RGB contract. That was the original idea the RGB technology was developed with like a year ago, and the idea that I started working with. There is one problem though, which actually required to make the whole story much more complex. It is that you can own multiple assets, like USD Tether, Euro Tether, whatever, some collectibles, I don't know which tokens, identity profiles. And actually, these channels are, these assets, they are assigned to some Bitcoin transaction outputs. It's the way RGB works. And you can assign multiple different assets to the same transaction output. And you can also assign, you can also have a multiple, like coins in Bitcoin, you have a multiple coins per address. You can have a multiple coins of assets per asset that you own, and they may be assigned to different transaction outputs or even to a single transaction output. And you need to do a deterministical commitments. When you transfer one of those assets, the rest of assets has to be moved as well. And you need to put a commitment into the transaction that spans that output. But with the deterministic Bitcoin commitments, you can put only a single commitment. And basically you got this complexity. Once you move from a single asset to multiple assets, you get this many to many complexities, which are basically unmanageable, both in terms of keeping the proof size compact and doing the proper validation without running into a risk of breaking the whole security model. So that's why we had to introduce another layer, which is named multi-commitment, that's sharding layer, which basically abstracts the assets from each other and allows this complex functionality. And this sharding layer, it isolates histories of different contracts without a risk of double spending. It is defined by LNPBP4 standard. You may look into it if you're interested. And because of that, we had to introduce another level of complexity into RGB itself, the stuff that we name anchors and stash. So basically with RGB, when you have a contract with some asset and you have a state transitions, it's actually like Bitcoin transactions. For RGB assets, you have state transitions, which define where you move this asset under only this specific contract. So state transition can move only a single asset and relate to a single RGB contract. They are all isolated from each other. But because at the same time, when you move them, you have to move other assets, and the proof about the history related to the deterministic Bitcoin commitments, it should include information about all of these state transitions. We introduce a concept of anchor, which actually links to many state transitions in a way. So it's not state transition links to anchor, but vice versa. And the anchor can contain partially revealed data, so you will be able to verify history of one single contract without even knowing that other contracts there was involved. And the anchors is basically the structure that keeps these proofs about sharding and about deterministic Bitcoin commitments, and it is separated from the state transactions and from RGB contracts, because basically anchor, as I said, can be related to many different state transactions under different RGB contracts. And the stash is basically a combination of all these things. So you have RGB contract, you have, for each of them, you have a graph of state transition, and you have, additionally to that, an anchors that cross-link all of these state transitions and contracts sometimes. And put all together, it is named an RGB stash. A thing that have to be kept very carefully. It is a critical thing. If you lose your stash, you lose all your assets in that stash, if you lose that data. And this is what wallet software is actually keeping. The important thing that stash covers all the information about all the assets that you own. When you would like to make a transfer, you don't need to transfer the whole stash, because it will, like, you pay just one coin to somebody else, and you don't need to reveal all the information about all coins you have and even other coins. So in terms of transfer, and also a single transfer is not enough. So you can send a state transition to other party, and it wouldn't prove him anything. The other party needs a history, and to prove the history, it needs a related anchors. So when you do a transfer of RGB asset, you basically take your stash and extract a partially revealed history from the stash. It's quite a complex operation where all the data that are not important to the current transfer are ignored and hidden behind the different things like confidential amount, mechanization, transactional put blending. There are actually 4 technologies that allows you to hide the data. So you construct and you skip everything that is not important to the coins that you just transferred. And this history, partially revealed history, very compact form of it, is named a consignment. And you take this consignment as a single structure, and you send it over network by other means to the party that is receiving coin. And this consignment is then verified by that party with all this partial data. It is still able to verify the history without seeing all the data there. And after it is verified, it is merged into the stash of that other party. So he will be able to keep the history inside his stash. So that's the basic workflow of how RGB is working with the multiple assets. And while when we at the beginning had a very simple thing, like we have some off-chain proofs and the history of them, and we send it over network and that's all, here we will have to come, when we move to multiple assets, we have to come with this more complex concepts of transitions, anchors, stashes, consignments, and so forth. But if I will put all together onto the slide, it will be still very, very complex to understand. And to explain that, I have to explain separately such parts as deterministic Bitcoin commitments, as single-use seals. I will be spending this time today, and how they are integrated at the level of client-side validation and into the RGB and parts of the RGB protocol, which will be the next week. So let's solve the complexity of RGB by taking a step-by-step approach with defining these 3 paradigms and the way the RGB using these paradigms one by one. I will make a small break. Do you have any questions?
Yes, we do.
All right.
There was a question from Martin, and he was wondering how fees are handled here. Would it be possible for a user to hold a token and send it around without having to hold or manage Satoshis?
Well, basically, the fees, we have two fees. There is no transaction fees at the level of RGB. However, the asset issuers may define existence of such transaction fee with a schema and some simplicity script. In terms of any transition and transfer of assets, we still have a Bitcoin fees, Bitcoin network fees, which have to be handled by Bitcoin wallet. And the SDK we are developing for RGB, the high level, it will be shipped with some coin selection and fee handling automatization mechanics, quite simple one. And there will be opportunity to wallet developers to compete and to provide some more advanced coin selection and fee definition mechanisms at the level of Bitcoin transaction, not of RGB itself, of course. Does it answer the question?
If I may, Maxim, there may also be, in case you are transacting over the Lightning Network and not over the base chain, in that case, there will be, of course, the Lightning Network fees for possible routing or exchanging, but it's more complicated. But in on-chain transactions, you just have the block space fees.
Well, with the design proposed by René Picard for RGB, we will be able to have fees for Lightning Network transfers in RGB tokens itself, not in Bitcoins, because we will have a single asset, either Bitcoin or one of RGB assets per channel. And all the funds will be managed in terms of that asset, meaning that if you have a USDT channel, you will pay a fee with USDTs.
Reasonable.
Inside the channel, yeah. Okay, let's move forward. We actually already nearly an hour of the presentation, and I just made halfway through it, but I don't know, is it worth continuing or we shall continue the next week? What would be the opinions? Is there actually 1/3 of the presentation? Shit, it's a long story.
1/3 probably. Other 2 hours are probably unpractical. So in that case, it will be better to arrive to a point that you feel can be a little bit self-contained, and then to split to the next time. And to anyway, everybody can still watch everything in the same single marathon if they want.
All right. Okay, I will continue, and maybe in half an hour I will just come to some section where we will break till the next week, and I will start with that part from on the next week. I will continue from that point. So the first paradigm is commitments and the application of the commitments to Bitcoin blockchain, which we named deterministic Bitcoin commitments. It's basically a zero footprint, provably unique commitments embedded into transactions or their components. I will explain each of these parts. So basically, zero footprint means that the size of transaction or any of its components is not increased. And commitments means that there is no information can be extracted back from without additional data and information from the transaction or any of its part, and it is impossible to know that there is a commitment until you get some proof of this commitment existence. Provably unique means that you can prove that there is only a single commitment in particular transaction or a component of the transaction, and you can prove that there couldn't be any other commitment made with the same transaction or its component under some specific protocol. And embedded means that basically you embed information, but without this property of being able to extract it back. And it works with both. It works like at any level of the transaction. So we have a stack of procedures and stack of standards which explains how these deterministic commitments are applied at each level. So these standards are LNPBP1, LNPBP2, and LNPBP3. We have commitments that are put into public keys, into Bitcoin script, into transaction output, and into transaction. It is more complex. I will be showing you on the next slides. We were thinking that it's that simple, but it's not that simple. And it is based on the paradigm of commit, embed, verify scheme. You can look into this module. There is a lot of comments, document comments inside the code, so you can understand it better. The actual commitments are implemented into BP-DBC module, again with the comments, and they rely on Bitcoin scripts module for automating quite a complex workflow with Bitcoin scripts, parsing them and so forth. I will be covering this in this on the next slides inside this section. So I just describe this slide on the title slide. Is basically what it means to be provable unique, hiding, zero footprint, and client-side verified. So creation and verification of the commitment in terms of client-side verification require extra transactional information. The terms that are related to Bitcoin commitments. Basically, it's important to understand that these terms are not part of RGB itself. It's part of underlying protocol. So in RGB itself, we reference to them sometimes, but it's not a part of RGB spec, just to distinguish these things. So in terms of deterministic Bitcoin commitments, we have a container and a commitment. The container is the data structure, provided all necessary information to hold the commitment and construct it, and the commitment is actually the resulting transaction, or its part, containing the embedded commitment to the message. The interesting thing that from a side party, they can't be distinguished from each other. It is only known from inside the code, which actually either creates it or verify with some additional data. This additional data are included into container. So the container consists of the host, the target transaction with component for embedding commitment, and some external data to that transaction. Basically, this external data consists of the proof, an important part, that have to be persisted and kept. If you lose the proof, you wouldn't be able to demonstrate that the commitment existed. You wouldn't be able to prove that you have created this commitment. So it's mission critical part of the data, extra transactional data. And there is a supplement. It's another part of extra transactional data which are not critical to be kept. That's why I introduced the specific terms, and everywhere in the code, even if from the developer perspective, it will be easier to join this data into a single structure, it's separated everywhere throughout the library, meaning that you have to manage this data differently. The proof have to be kept, no matter what. The supplement is not necessary. It is required for verification and the commitment, but this data can be reconstructed, not from the transaction itself, but from transaction graph or from some extra information like that one is available from genesis of the asset issuance, for instance. And this information is publicly available, and you don't need to keep that. You just need to have a trusted source. I will be introducing with the client-side validation next week the concept of trusted source. So you need to have a trusted source to getting supplement, meaning a trusted source can be a Bitcoin core node you trust. And you trust that the transaction graph provided by this Bitcoin core is valid and included in the longest chain. And you use that transaction graph to compute the fee, which is a part of the supplement. And then you use the supplement together with the proof you kept to be able to prove the commitment itself. Or a Lightning node is another example of a trusted source, because you can take the same information about the fee, not from Bitcoin Core, but from the Lightning node. In both cases, you have the single API to them from the RGB. So that's data decomposition for deterministic Bitcoin commitment. I just probably described the slide. So there is, for external extra transactional data, there is persistent and recomputable part, proof and the supplement. And the proof must be created before the commitment by the wallet or other software. So it's not a result of the commitment procedure. It is created before the commitment, and it becomes the part of the container. it have to be persisted, and it consists of the original value of the public key and additional data. So sorry, I used supplement here, but again, it should be different word. That's why terminology is important. Consisting, it's called script information, consisting of either script source, original script source, or a hash of the top script root, which is different from taproot, for taproot-based output. Sorry, there is a plenty of poor terminology with both witness and taproot, so there is a difference between script root and taproot, but I wouldn't be explaining it here. So it's not optional supplement, but script info structure. Okay. And recomputable part consists of transaction graph based information. It is fee, basically, and from RGB genesis data, because there is some protocol-specific tags and entropy defined for each issued asset to prevent other party from guessing where the commitment can be residing. And why supplement is still important, even if it's recomputable and you don't need to keep it, the reconstruction may take quite a significant time or require you to be online to be able to talk to Lightning Network or Bitcoin Core. So it is, while the supplement is not critical, it is still advised for many wallets to keep the supplement. But supplement have to be kept separately from the proof, just to avoid any chance of proof discarding or pruning together with supplement data. That's the workflow of deterministic Bitcoin commitments, linking all these terms together. So there are basically two stages. The commitment stage, for these commitments, we name it embed commit, because with the normal commitment, you have a message and you create commitment from it. With these commitments, you have a host, basically not even a host, but host inside a container, and a message at the beginning, and you embed a commitment to the message into the container. So we name it embed commit to distinguish from simple commit procedure. So there are two stages. So the first stage is embed commit, and the second is verify. At embed commit, we construct a container with operation named construct. So at each level that you will be working with DPCs, transaction output, script, public key, and others, you will have a container which is specific to the level. And all of these containers will have a construct function, which basically takes the data from external sources. For instance, you compose transaction, a normal Bitcoin transaction in your wallet, and you provide it to construct the container. And a message, again, it is outside of deterministic Bitcoin commitments. What is the message? RGB will provide the message, and in the case of RGB, the message is actually a hash of serialized state transition. But we will be covering that later. And then with the container, we can do basically two procedures. The first procedure is embed commit, when we actually embed the commitment to the message into the container, and as a result, get a commitment. And the commitment is something that we can publish into Bitcoin blockchain or to Lightning channel. Basically, it is a transaction or transaction output or public key or something, depending on the level, which actually you don't need to keep it. You have to publish it into underlying transaction graph system. And that's a commitment. So when you create a commitment, unlike many other cases, you don't need to transfer commitment to the other party with the asset transfer. For the other party, you have to use a proof. And to get the proof out of container, you use this deconstruct procedure. It actually separates the container into the supplement and the proof, as I just described. Now, you transfer the proof to the party you would like to prove the fact of deterministic commitment, and the party runs a verification workflow. It again takes the message from somewhere else. It's outside of DDC procedure. In terms of RGB, it will take a state transition, serialize it, and it takes the proof. Next, it reconstructs the supplement. It reconstructs the supplement as I have just described, using some external trust source. And it gets with this reconstruction, it creates a gain container with the reconstruction procedure from proof and the supplement. So here we separate the container into proof and supplement with a deconstruct, and here we have reconstruct operation to to put container back from proof and supplement. And then having a container, the message, and taking the commitment from the transaction graph, like a transaction itself, from a trusted source. We run a verify procedure with these three components, which either it can fail, because, for instance, it wasn't provided a properly constructed data, or return true or false, meaning that the true, it is the commitment is valid, it was created, it is the data, the message you have is actually committed with this commitment, and false if it is not, if it is a wrong message or a wrong transaction. And you never know what is wrong with that. But basically, you should not trust this commitment. So in terms of error, means that you've done something wrong. False, it means that you was fooled. And true means that the information you got is correct and valid. For doing that, we have a set of interfaces defined. Basically, this, first of all, it's at the level of paradigms. We'll have a commit verify module, having embed commit verified trait, basically at the interface description with these two procedures, embed commit and verify. You have no other procedure. And with the deterministic Bitcoin commitments, actually, when you run a mission critical code, it either commit verify or verify procedure. And at the level of deterministic Bitcoin commitments, we have a type-defined container, and I already described that it has reconstruct, deconstruct operations, and operation that allows you to get the proof without supplement if you don't need a supplement. There is an important data structure, which is basically proof. Proof, it is, while at the different level of script deterministic Bitcoin commitments, we use different containers and different supplements, the proof is the same data structure for all levels. And it consists, as I said already, from original public key and from the script info, which is basically depends on the particular transaction output structure. There might be three types of script info related to if you have a single public key, no matter how you serialized it, even through if you're doing even a pay to script inside pay to W witness public key hash, you still don't need to provide script. You have just a single public key is enough. It is original public key before the commitment operation. If you have any type of scripted output, you use a redeem script structure with the source of redeem script or witness script. I will cover the difference later. And taproot, for taproot, you have a special structure with a tap script root hash. How the commitments are working at different levels. This is the slides from Milana presentation last year. Nothing has changed here, mostly. So we have this procedure. I wouldn't be stopping here. It is well described in the standard. It is described in code. It can be seen on the slide. So basically, we use special tags, hash. We create HMAC hash of the message together with the original pub key. Committing to the original pub key, we create a tweaking factor, which is being applied to tweak pub key. We have three to a pub key to obtain tweak pub key. We have three cases where the operation can fail with a very, very, very low probability. But again, we're covering them with the proper error messages. At the script level, we have a bit different problem, because the core concept of uniqueness of the commitment is that we have to commit inside the public key not only to the message itself, but also to the original value of public key. Because public key commitments, they are gamma-morphic. The tweaking procedure is gamma-morphic. And if you commit to a single message to a public key and then to a second message with the same public key you get from the first commitment, you will be able to verify the commitment against both of these messages. Because it's like addition, you can change the order of the commitments, you can do multiple commitments. But we need a singular commitment so that you can commit only to a single message, and any other message you committed before the last commitment would be invalid in terms of verification. And we're doing that by committing to the original value of the public key. And it works well when you have a single public key, but it doesn't work well when you have a scripted output. And in terms of scripted output, after many different approaches, trying many different approaches, we ended up having this idea that basically we extract all the public keys from that output using mini-script determinism. And even if there is some hashed public keys, we need to know the original public key behind that hash. We add all these keys together, basically obtaining the sum. We tweak only one of those public keys, but in that tweak, we commit not to the original value of the public key, but to the original value of some of those public keys. And it will make us sure that only one of these public keys can contain a commitment, and the commitment is really singular. That's what is being described in LNPBP 2 standard, and we name that if the original LNPBP 1 is key-based, public key-based commitment. This is a public key set-based commitments. There is one side note, maybe I will run over it because it will be hard to continue from this start point next time. It's basically the Bitcoin script type hierarchy and transformations is very complex. I will quickly cover it. It is very interesting section for wallet developers, and mostly it's self-explanatory in the slides. So I will run through them. If you don't understand something, you will be able to take the slides later and to dig through it. So the life of Bitcoin script. We start with either single public key or some script template like mini script or any other, and set of public keys and pre-images you would like to use in that script template, descriptor, whatever else. Then we decide on script pub key representation type, meaning it can be explicit. So we embed an open script or open pub key. It is named in Bitcoin Core bar representation, explicit representation. We can use a key hash, we can use a script hash, we will be able to use taproot, we decide on that. Then we need to decide, would we use SegWit or not? In some cases, we will be able, in some cases, we can't use SegWit. For instance, if you would like to have an explicit representation, we can't use SegWit. And with the taproot, it will be even more complicated. And you end up with having all these encodings for a public key, for not a public key, but for the whole set of scripts related to this specific transaction, including SIG script, witness, and other structures. And if you have a single public key, you have this workflow. And for a script, you have this workflow. And if you put it all together, it's just a mess. It's the number of steps you have to take, because we had to cover all this mess while we was doing a script-based commitments. And basically, once we've done that, it may simplify life for wallet developers at Bitcoin level itself, not on at RGB even. So what we ended up is that basically I have designed a strong type system and algorithm workflow. Here is the type system. There are types related to hashes, and these types are already in Rust Bitcoin, and that was the type system I was talking at the beginning of today's call. And so these types that are getting to Rust Lightning last week with the PR that I've made. Basically, we have a hash of pubkey, we have a hash of script, we have versions of them specific to witness. Interesting that with witness, you basically end up frequently using both of them. And we have a types of scripts. Basically, there is the pubkey script, everything that comes from script pubkey of the transaction output. There is SIG script, again, a representation of content of the SIG script field of the transaction input. There is a witness, a representation of witness field of transaction input. And these types we know from Bitcoin. However, there is a few more. There is a redeem script, reconstructed from either SIG script or witness, depending on the structure of the whole graph. There is a witness script, which is basically different from redeem script. In some cases, would pay to SH, would pay to witness public key hash or script behind pay to SH. You have both of them, both redeem script and witness script. You have a tap script with a new taproot system. And after that, I had to introduce a new type, which I called log script. Basically, it is a script which we really need for RGB, and it is a version of all the scripts, or a script reconstructed from all this data, which contains complete set of all public keys in their explicit form. And with that script, we can make sure that we really create a deterministic Bitcoin commitment. Additional to those types, there are other types, which is witness program. It is different from the witness data structure. There is witness version, because we have right now witness 0 version, Taproot is a witness 1 version, and probably there will be more. There is 17 possible witness versions, not 16, 17, because we can't start starting from 0. And there is a conversion strategy. Basically, the way we code the log script into other types of scripts for both transaction outputs and transaction inputs. And with the SIGWID, it's quite funny that with the SIGWID, we have such terms which are completely different from each other, and it's important not to mix them. There is a witness version, there is a witness program, there is a witness, which is not a witness program, there is a witness script, which is not a script, there is a witness 0 version 0 script hash, and witness 0 version 0 public key hash. And this all different data structure. Here, this slide explains how they are interrelated. And when you have a pay to script hash into pay to witness public key hash or script hash into public pay to script hash, you have even more complex system, which is shown here, how all this serialized and works. And it's all being recreated in the BP module of LNPBP library, BP scripting. So we have this workflow for creation, parsing of transaction scripts, outputs, inputs, and committing to any kind of transaction. And the workflow is that we still start with the source data, then we construct a log script, which will become a part of the proof I just covered. Then we decide on the strategy, on the conversion strategy. And with the conversion strategy, we get a pub key script when we create a spending transaction, or when we need to spend some output, we can reconstruct redeem script and optional witness script, and from them make a SIG script and witness for a transaction output. And here is the single data structure that we have to store for cases like RGB or wallets that use unstandard scripts. They will need to store only a log script, and the rest can be reconstructed from a transaction graph and log script information. So that's why we needed to design all this system to get RGB working. And we need to embed commitments into scripts, because without that, we wouldn't be able to support a Lightning network. This is scripting workflow. I wouldn't go into much details. It shows how these types are interrelated and with which procedures you can transform one types into others. And basically, we all use that for doing LNPBP script-based embed commit procedure. The next challenge that we had is to embed commit, for embed commit is to put this transaction output with a commitment into transaction itself. And for doing that, we basically, we were able to select some simple scheme, like always use the first transaction output. But we would like to make sure that we maintain the perfect level of privacy. And none of the chain analysis tools will be able to guess which output may contain the commitment, even if it wouldn't be able to see it, because we're quite sure that there will be leaks of these proofs, of this private data, of the state, and people will try to reconstruct that. And we need to make this task as much complicated as possible. So the idea is that, and at the same time, we need a very deterministic procedure, because if you don't have a deterministic definition of the script output, there could be a multiple independent commitments, and you can just do a double spending with that. So we've taken two data which are not part of the transaction itself. But this data can be reconstructed in a deterministic way, the same way by all parties running verification of the commitment. The first piece of this data is coming from blockchain graph, and it's actually amount of used fee. It is committed by the transaction, so you can't change it, you can't fake it. You need to just an access to the transaction graph, either at Bitcoin Core or Lightning node. So we need an external service for that, and that's why it has become part of the supplement. And the second part is a protocol-specific information, which is protocol-defined random value. Well, we basically take as this random value a hash of genesis of some asset. Again, it is publicly known information. The genesis is published by the issuer, but it is different for each of the assets, meaning that with that, if the transaction have several outputs with a quite a high probability for spending each of the assets, your commitment will get into different output, and it will help to maintain the smaller size of all the generated proofs and the rest of the story. So, and when you have a transaction, and for instance, quite soon we will have like hundreds or if not thousands of contracts and assets issued with RGB, and it means that if you have any transaction with any number of output, you wouldn't be able to guess where which commitments are, because with the different hashes of these contracts, you have a linear probability that any of these outputs can be part of the commitment. And you can't, test all the existing contracts against all the existing transaction outputs, because the Cartesian multiplication of these two sets would be just unmanageable. So with that, we were able to achieve quite strong privacy level, however, at the cost of the requirements for this supplement, which can be reconstructed from the transaction. So RGB needs a Bitcoin core server, Electrum server, or Lightning network behind it to provide this information. And there is a proof, actually, which I already have explained. The procedure runs following. First, you have to construct original transaction. Like the way you'd like to construct some transaction, just construct a transaction. It can contain any outputs, inputs. Then you find out for a particular asset, particular commitment, which output you have to use with the current level of fee. And it's not important because basically you don't need to be owner of this output. It can be another party owning this output. The only thing it needs to know is that it needs to know the original data to be able to spend it. You can, for instance, another problem we had with the Lightning network, the original idea was to adjust the fee to put the commitment into the desired output. However, the problem that if you have a deterministic ordering of transaction output, which is made by many wallets, and for sure it is part of the Lightning network specification, so both nodes generate the same order of the outputs, you order them according on the values of the amounts in that outputs. So when you adjust the fee, you're basically taking some satoshis from some outputs and you reorder outputs. And while you're trying to, with the fee, to get into a specific output, the moment you adjust the fee, you get this reversal dependency, and you have to run multiple tries until you get lucky. Even worse, when you get the output and you apply the tweak, you change the public key, meaning that you change the value of script hash or public key hash, and that output meaning again that you can change the order of the deterministically ordered transaction, and it makes you impossible to do what you need. So basically, that's why we ended up with tweaking the output that is already defined by the fee, and not trying to adjust the fee to change the output number we are committing to. Then, once we've done that, we do the actual commitment. We run through whole hierarchy of deterministic Bitcoin commitment stack, and then we update this particular output, and we have a transaction with the commitment which we can sign or publish. So in terms of this commitment hierarchy, we have 3 standards covering different parts of this hierarchy. It runs from transaction to transaction output into script pub key. And depending on the construction of the script pub key, it can go into branch of public key commitment or log script commitment or top root commitment. And with the log script commitment, we have a commitment into key set. And we have the supplements and proofs, which are used together with deterministic Bitcoin commitments. So the last 2 slides, a cool example doing all this stuff. So here we construct a container, transaction container. It's shown at the top level of the transaction. We constructed providing all this information about protocol factor, protocol type, desired fee, well, actual fee that will be used, that is used by transaction, which we provide here. We provide all the public keys involved. We provide the public key we would like to tweak. It is the second public key. And we provide script info sufficient for reconstructing the whole script. It is composed, you see, it's quite complex. It uses 5 public keys with some, it's basically constructed from mini script. And we say that we would like to compose that into a witness script hash behind the pay to script hash thing, which is quite complex. Then we have a message we would like to commit to, and we create commitment from the container and the message with a simple procedure named embed commit. We get this commitment. We get the witness transaction from the commitment, and we can publish it to Bitcoin network. And then we deconstruct the container into the proof and supplement, and we keep the proof for us and send it to other party when we would like to prove. The other party, when it'd like to verify the proof, it actually takes the proof and it creates a transaction supplement from protocol, factor, fee, and tag, which is publicly known information. So it reconstructs the supplement and then reconstructs container from the supplement and the provided proof. Then it reconstructs the commitment from the Bitcoin blockchain transaction taken from Bitcoin Core or Lightning channel or wherever it is, and verifies the commitment against the container and message. And it either gets true or false, or error, meaning that something done in a wrong way. It's all in the library and it's all working and passing tests for now. I mean, in the refactoring branch of the library I was talking at the beginning of the presentation. And this is the last slide for today. So I would like to summarize the deterministic Bitcoin commitments with these terms defined: container commitment, host, proof, and supplement. I wouldn't be repeating it. It's for the written version of presentation, so developers and others may always check this, and if they forgot what proof is about or supplement is about, to see it here. So I think that's all for today. And the single-use seals and other parts I will leave for the next presentation. So the next time we will have single-use seals, then client-side validation explained, how it is related to single-use seals and other commitment technologies, how RGB is structured and why it's structured in that way from these components, and what is contract genesis, allocations, transitions, anchors, consignments, and stashes, again, at data structure level and API level. How confidentiality in RGB work, what is fully disclosed and partially revealed data for transition seals and consignments, P2P protocols related to RGB, RGB wire protocol, LN protocol integration, and the Spectrum, which is also a P2P protocol, fungible assets API, how you can simply work with the fungible assets, and hopefully we will start, probably we wouldn't have time next time, but at some point we will do a presentation of RGB SDK, which includes kaleidoscope, wallet, BP, LNP, and RGB nodes are Rust-based, which are required to run self-hosted RGB or hosted RGB backend, and RGB wallet SDK. And that's basically will be the next time. Thanks for your attention.
Great, thanks.
Thank you. Much appreciated.
Very, very good job. Thank you. And we receive, okay. Guys, I think if you have any questions, you can just speak up now. Feel free to do that.
So I'm kind of curious about the asset issuance on RGB. So if you have the Lightning passing through on RGB, like where did the fees come from for that?
Again, for Lightning, for paying for Lightning transactions, you use your asset. You pay fees in the asset you transact.
Okay, so if it was a created asset, it wouldn't actually touch the base layer chain at all for transaction fees. You can actually have your stake complete in the asset.
Well, you still can use Bitcoin to construct the fee for transaction in terms of the transaction fee, but you are compensated for that amount of bitcoins in the native asset of the channel.
Okay, perfect. Thank you.
Yeah, I have a question. Last week we were discussing in the call whether there should be kind of extensibility for schemas in RGB.
Yeah.
Did you reach an answer to that? Or
well, the idea that I was going to propose, and probably we will be discussing it on the next call, is basically that at this stage, we may not take a decision regarding this part of the specification and take more time to find all the security implication of it, because basically with a schema, you validate a contract against the schema. And right now, you don't have a procedure to define if one schema is superset or subset of another schema. But if you will add this function later, it wouldn't break the consensus or it wouldn't create a hard fork, because basically it will be depending on whether or not wallet would like to do it for its own. So even if you will be able to provide this procedure, it will be later when we will make sure that it's part of the best practices and doesn't creates any security leaks. But the first version of RGB will be shipped without such procedure. Any other questions?
Hi, can you hear me?
Yeah.
So I had an idea that might be interesting, but I'm not sure if it makes sense to issue an asset that pretends to be like whatever else, but actually is a Bitcoin, and with the purpose of achieving higher privacy. I don't know if this would add any value, or I'm misunderstanding something.
Well, it is possible to be done, but the economy will be that you have to trust the issuer, that it maintains the reserve. But for sure, we've been having this idea for some time for now. So it may have some marginal applicability for doing more confidential transactions or something.
Ah, great. Thank you.
Of course, you need a redeeming scheme like Liquid, like another kind of redemption sidechain scheme.
Yeah, basically there should be a centralized provider which will be giving you that asset or taking it in exchange to your Bitcoins back. And you can't do that in a decentralized way. So at the best, this provider can be federated.
Yeah, I was expecting that, was thinking mainly about smaller values or limited risk cases.
Yeah. Yeah, well, RGB provides quite advanced way for privacy and confidentiality. Unfortunately, as anything that is being issued other than Bitcoin, you always have some issuer. And while RGB allows you to have a decentralized and censorship-resistant secondary market, if the value of some RGB-based contract is bounded to the issuer, like issuer maintaining its reserve, you're still dependent on the issuer in terms of value maintenance, while you will be able to freely transact. So with RGB, the issuer wouldn't know about the transactions or the asset it issued. It wouldn't know about the owners, so it's a pure bearer rights, but it wouldn't be able to censor it. Even Bitcoin miners wouldn't be able to censor this because they wouldn't see that there is something in the transaction. And it will be very private. But again, the underlying value of this contract and asset will economically, not technically, depend on the issuer.
There was, I mean, this will be a little bit off topic compared to the call, so maybe we will discuss it another time. But just to mention it, there was an idea that I was discussing with Maxim and other people many months ago of a possible kind of decentralized way to do that, which is a one directional proof of burn. So you burn Bitcoin to generate the RGB asset, and then you have some kind of demurrage to guarantee that the economical price of the one-way peg stays kind of the same of the other way. But it's probably doesn't work. I mean, we could experiment in the future eventually.
Yeah, and there is another interesting option that you can basically use a multi. We don't have them now, but let's say that one day we will have multi-peer Lightning channels. It's kind of better way of doing sidechains where basically you don't have N of M, but N of N, meaning that you can't do there any fraud. And with this multi-party Lightning channels, you will be able to issue assets that will circulate inside that multi-party channel. And within that multi-party channel, it will be decentralized in terms of that specific channel. But it's kind of very, very, very far future. Any other questions?
I think we can wrap this up for now. I will upload the presentation to the GitHub with the reference to the Telegram chat. And we'll continue with the chats, with this chat next week. And if anyone has any questions, you can either drop me a message or go to the GitHub and check everything we have. Yeah, and see you next week, guys. Maxim, thanks very much for the presentation. Thank you.
Thank you very much
for joining.
Thank you. Bye. Bye.
Bye. Bye.
Thank you.
Bye. Thank you.
Thank you, Maxim.